Hello guys, and welcome back to my YouTube channel. In this video, we're going to be going over how to draw the chair conformation of cyclohexane. So cyclohexane, where cyclo is referring to the ring, hex is referring to 6 carbons, and ane is referring to the fact that there is only single bonds. So here we can see, if we count the carbons, there's 1, 2, 3, 4, 5, 6 carbons in a ring, all connected by single bonds. And we're going to be drawing the chair conformation of cyclohexane. So this would be the chair. And specifically, this would be the right-handed chair. We're going to be going over how to draw right-handed chairs and left-handed chairs. But first things first, we don't want to just have to memorize the chair, so let's learn how to actually draw it. And there is a step-by-step method to drawing the right-handed chair and to drawing the left-handed chair. But let's start with drawing a right-handed chair. So the first thing you want to do, and there's multiple ways to draw chairs, but this is just how I've always gone about it. I like to draw a big, wide V, okay? So if a V looks like this, I'm going to draw a big, wide V. Now step 2 is that from the right-hand corner and the left-hand corner of the V, so here and here, I'm going to draw 2 lines going down at a 60-degree angle, and both of those lines are going to be going down to the right-handed side. See, we're doing a right chair, so see if we can see the trend. So we're going to notice things are to the right. So these 2 lines that I'm drawing down at a 60-degree angle are going to be slightly slanted to the right. Now, I'm going to draw a dotted line that divides, and this is an imaginary dotted line, the 2 vertical lines going downwards that I've drawn in green. Then we're going to go to step 3. So now all that's left to do is clearly connect the bottom 2 points of the vertical lines. To do this, all we have to do is draw an upside down V, okay? So if the first V we drew was blue, and it was a regular V, with respect to the dotted line that we made, the kink in this V, we can see is slightly off-centered to the right. So now, for connecting the bottom 2 halves of the vertical lines, all we have to do is draw an upside down V that's slightly off-centered to the left. So here we can see this upside down V is slightly off-centered to the left. That is it, that is all. That is how you draw the foundation of your right-handed chair. So in summary, step 1 would be to draw regular wide V. Step 2 is to draw 2 lines downwards at a 60-degree angle, slightly slanted right. And now I guess our step 2.5 would have been to draw in our imaginary dotted line. And that brought us to step number 3, which was to draw an upside down V off-centered to the left of the dotted line. Now, once again, this is just one way of drawing a right-handed chair. This is how I always did it. I find this is the quickest way to do it. Okay, but the thing is, we're actually not done just yet, because if we look at cyclohexane, each of the carbons is attached to 2 hydrogens, because every carbon must make 4 bonds. Therefore, we must draw in 2 hydrogens connected to each of the carbons a part of cyclohexane. That means we somehow have to put in 2 hydrogens on each of these carbons as well. So this brings me to showing you how to draw axial and equatorial bonds on the chair. So we're going to start off with drawing in all of our axial bonds. So first things first, we're going to go over how to draw axial bonds. So axial bonds are going to be bonds that point up towards the sky or down towards the ground. So let's reference sky and let's reference the ground. So starting at the top right corner of the chair, so this carbon, and once again, this is going to be arbitrary. You could start at any of the carbons, but in most textbooks, it's most conventional to start at this top right-handed corner. And we're going to draw one vertical line going up towards the sky. Now, going clockwise around the chair, I'm going to label the carbons.
1 to 6. 1, 2, 3, 4, 5, 6.
So since I drew an axial up, why is this up? It's because I point this bond up towards the sky. If you extended that bond off into infinity and beyond, and I'm going to alternate up, down, up, down, up, down on each of the carbons. So I either point up towards the sky or down towards the ground. So on carbon number 2, I'm going to draw down towards the ground. And then carbon number 3, I'm going to draw up towards the sky. Carbon number 4, since carbon number 3 was up towards the sky, would be down towards the ground. Therefore, say it with me, carbon number 5 would be up towards the sky. And then carbon number 6 would be down towards the ground. Bada bing, bada boom. That is how you draw in all the axial bonds on your chair. So now, let's really nail in this concept. So 3 of these bonds point up towards the sky. If we picture this chair as a 3D object in space at the park, for say. So the blue bonds, and I'm talking, we got to use our imaginations here. If we extend these bonds off to infinity and beyond, all these bonds are going to reach up towards the sky. Whereas the 3 bonds that I'm about to draw in green, if we extend them to infinity and beyond, they all go down towards the ground. So now, in summary, bonds that are axial that point up towards the sky are called axial up bonds. And bonds that are down axial are called axial down bonds. And now this is a very important point that you cannot forget, because we're going to have to determine the difference between an up bond and a down bond later. But we're not there yet. Now we have one more thing to do. We just drew in all the axial bonds. So now we actually have to draw in the equatorial bonds. Why? Well, let's look at carbon number 1. Carbon number 1 currently has 3 bonds. 1, 2, 3. And every carbon must make 4 bonds. So we need to add in one more bond to all of the carbons so they all have 4 bonds, because we want every carbon to have 4 bonds. So now we're looking at drawing equatorial bonds. I'm going to redraw in all of our axial bonds, starting at the top right corner. Up, down, up, down, up, down. Okay, so now to draw my equatorial bonds. To draw the equatorial bonds of carbons 1, 2, 4, 5. So these would be the corner carbons. I want to extend both my back V and my front V to infinity and beyond. So extend these bonds to infinity, to infinity. The downwards V would go infinity, but down, infinity, but down. So now, all you got to do to draw in the equatorial bonds for the corner carbons, so carbons 1, 2, 4, and 5, is draw a line equal in magnitude to the dotted line, but oriented in the opposite direction. So if your dotted line is going up, you must draw your equatorial bond going down. If your dotted line is going down, you must draw your equatorial bond going up. Corner carbons. So here, I would need to draw a line going down towards the ground. But on carbon number 2, the dotted line goes down towards the ground, so I must draw my bond up towards the sky. Carbon number 4, down towards the ground. So therefore, my bond must go up towards the sky. Carbon number 5, the dotted line goes up towards the sky, so I must draw my actual bond down towards the ground. That's it. That's how you draw in the equatorial bonds for all of your corner carbons. So now you just need to draw in the equatorial bonds for carbons 3 and carbon number 6. How do you do this? Well, these bonds are drawn in parallel to the vertical lines on the chair. So these two lines. You just must draw 2 bonds in the parallel position to these blue lines. So 1 equatorial bond there and 1 equatorial bond on carbon number 6. Bada bing, bada boom. That is how you draw in all of your equatorial bonds. But now we have to define which equatorial bonds are up and which equatorial bonds are down. So let's clean up our diagram and then do that. All right. Okay, I redrew in all the bonds in the same fashion that we just went over. All the equatorial and all the axial bonds. Earlier, we defined that there's going to be 3 axial up bonds. So these 3 bonds. And there's going to be 3 axial down bonds. The equatorial positions also have down and up bonds. So let's start at carbon number 1 and determine which bonds are equatorial up and which bonds are equatorial down. So at carbon number 1, what you got to do is you got to extend this bond. And once again, let's reference the sky and let's reference the ground. We're picturing this chair as a 3D object. So if we extend the bond at carbon number 1 off to infinity and beyond, who does it approach? The ground or the sky? It approaches the ground. And if things approach the ground, they will be in the down position. Equatorial down. So now, what about the equatorial bond on carbon number 2? This bond, if we extend it to infinity, who does it approach? It approaches the sky. So this would be equatorial up. Equatorial up. Carbon number 3, if we extend this bond to infinity and beyond, down. Down towards the ground. Equatorial down. Carbon number 4, equatorial bond up to infinity and beyond. And it's the sky. So equatorial up. Equatorial up. Now carbon number 5, this would be equatorial down. And hopefully you see the trend here. Now this equatorial would be equatorial up. See, we have alternated. We've alternated from starting at carbon number 1, down, up, down, up, down, up, bada bing, bada boom. So now we know where all of our equatorial down bonds and all our equatorial up bonds, as well as where our axial up and axial down bonds are. But we're not done yet. Currently, the way we've drawn this chair, when we don't draw on anything at the end of each of these lines, this indicates to the reader that that's actually a CH3, a methyl group. So right now we're trying to draw the chair of cyclohexane, so we must draw in a hydrogen at the ends of each of these bonds to wrap up this question. So redrawing in all my axial bonds, up, down, up, down, up, down. And then redrawing in my equatorial bonds, down, up, down, up, down, up. All that's left to do is draw in hydrogens at the ends of each of these lines. And that is how you draw the chair of cyclohexane. Alright guys, let's summarize everything we just talked about with an example that's a little bit harder than the last. So let's say our hexagon structure doesn't just have hydrogens. Now we got some substituents that are not hydrogen. Oh no, what do we do? I'm going to take you through the steps. Okay, step 1, always label, starting at the top carbon on the hexagon, 1 to 6 in the clockwise direction. Now once again, stick with the clockwise, but the carbon that you choose to start labeling at is an arbitrary position. I am just showing you the most conventional way to do this. So 1, 2, 3, 4, 5, 6. Now step 2 is you want to label all the carbons on your chair. And once again, you would have already drawn your chair in the same fashion that I showed you at the beginning of this video. So if you're still confused, go back and watch that again and again until it is more clear how to draw a chair in the right-handed position. So on your right-handed chair, starting at the top right corner, label these carbons 1 to 6. Once again, since I labeled the hexagon in the clockwise direction, I must also label my chair in the clockwise direction. 1, 2, 3, 4, 5, 6. Now, once again, where you chose to label carbon 1 is arbitrary. I could have started here. 1, 2, 3. Doesn't matter, okay? I'm just showing you the most conventional place to start. The only important thing here is that you label them both in the clockwise direction, okay? Okay. Step number 3 is I like to draw in all my axial and equatorial bonds on my chair, once again, in the same fashion that we did previously. But if you want to skip a step here, you really only have to draw in the axial and equatorial bonds on the carbons that have substituents on your hexagon. But for the purposes of this question, because we're still starting out here, I'm going to draw in all the equatorial and axial bonds. Up, down, up, down, up, down, down, up, down, up, down, up. Okay, there you go. All the equatorial and axial bonds are now drawn in. So now, take carbon 1 in your hexagon to be carbon number 1 on your chair, okay? So I'm going to label these guys in a different color. So let's make carbon number 1 green. And let's make carbon number 3 blue. All the other carbons, the substituents, are all going to be hydrogen. So I could draw these in right now. Hydrogens. It is only carbons number 1 and 3 that there's going to be anything other than hydrogen. So now, starting with carbon number 1, what we have to determine is if the substituent is on the up position or the down position. So listen very carefully. Wedges, wedge equals up, and yes, this one is kind of hard to remember, but just wait. But dash equals down. Dash, D for D. Dash equals down. So if you can remember that, then it's easy to remember that wedge is the opposite. So here the bromine is on a wedge, therefore it's in the up position. So it's in the up. So all you have to do is find the up position on carbon number 1. The up position could be axial or it could be equatorial. That's dependent on the carbon. Carbon number 1, we have an axial up and we have an equatorial down. So the up position is going to be the axial. So you'd put the bromine on the axial up. Now, what's the other substituent? Well, it would be a hydrogen that would be placed in the dash position. So dash equals down. So the hydrogen would need to go in the equatorial down position. That is it. That is all. So now for carbon number 3. Let's start off by honestly just drawing in that fourth substituent. So the hydrogen. Here, since the chlorine is on a dash going down, the hydrogen must be on the opposite. So it must be on the wedge. Wedge. Okay. Wedge equals up. So what is the up position on carbon number 3? So we have an axial up and an equatorial down. Okay, we just answered our own question. So the up position is indeed our axial position. So the hydrogen must go on the axial up. That means our chlorine must go on the equatorial down position. And that is it. This is how we would draw in all the substituents on a right-handed chair for this structure. Where the bromine is on the axial up, and the hydrogen is also on the axial up. And then this hydrogen is on the equatorial down, and this chlorine is on the equatorial down, axial up. Now, the next thing we must go over is how to perform a chair flip. Oh no, okay, these are actually not that bad. Let me show you. So let's continue with the same example, all right? So let's take our right-handed chair, clean it up a little bit, and then we're going to flip it to a left-handed chair. Okay, now for the purposes of the chair flip, I'm going to erase all of the substituents on carbons that don't have anything other than a hydrogen for simplicity here, because what we're really focusing in on is the non-hydrogen substituents. What happens to them when we perform a flip? So flip meaning going from a right chair to a left-handed chair. So this would be our left chair. And don't worry, I'm not going to leave you hanging. I'm going to explain what I did. So remember, in our right-handed chair, when we drew that dotted imaginary line, the back V was slightly kinked to the right. And our front V, the upside down V, the kink is slightly to the left. So on a right-handed chair, the back V kinks slightly to the right, and the front V kinks slightly to the left of this imaginary dotted line that we drew. In the left-handed chair, it is the opposite. If we draw an imaginary line splitting the two kinks in the V's, the back kink is to the left in a left-handed chair, and the front kink is to the right in the left-handed chair. And now remember, these two vertical lines were slightly slanted to the, say it with me, the right. So in the left-handed chair, our vertical lines are slightly slanted to the left. That is it. That is all. That's the only difference, okay? So that's how you draw your left-handed chair. It is in the exact same fashion as I showed you at the beginning of this video to draw a right-handed chair, but except the difference is the vertical lines are slanted to the left, and the back V is kinked to the left for a left-handed chair. And the front, the upside down V, is kinked to the right for a left-handed chair, which is the opposite that we see with a right-handed chair. So now, how do we perform a chair flip? So remember, we started labeling carbon number 1 to be the top right carbon on the right-handed chair. And then we labeled clockwise around the ring for the other carbons. For our left-handed chair, what we're going to do is we're going to draw in carbons number 1 to 6, but this time we're going to start at the position that's one carbon over in the clockwise direction. So carbon number 1 is going to be this position. 1, 2, 3, 4, 5, 6. To really nail this concept in, what if, because once again, this labeling is arbitrary. These are going to be kind of ugly chairs because I'm quickly doing this. For our right-handed chair, what if I started labeling right here? 1, 2, 3, 4, 5, 6. Because once again, as long as you label clockwise, it doesn't matter where you start. So where would carbon number 1 be on my left-handed chair? Okay, well, I have to start one position over in the clockwise direction. So I have to start there. 1, 2, 3, 4, 5, 6. So the carbon number 1, which is initially there, I now put here. So 1 over in the clockwise direction. That is it. That is all. Okay, back to our question. So now, take carbon 1 to be carbon 1 in both the right-handed chair and the left-handed chair. So the bromine is now going to have to be drawn in on our new carbon 1, and the chlorine is going to have to be now drawn in on our new carbon 3. So we might as well draw in all the up and down bonds, or all the equatorial and axial bonds, on the left-handed chair. So this one you can do in the same fashion that you do for the right-handed chair. Nothing changes. I'm going to erase all the bonds on the carbons that I don't need to care about right now. So carbons 2, 6, 5, and 4, just for simplicity, because we only care about what's happening to carbons number 1 and carbons number 3. Now listen very carefully. When you flip from a right-handed chair to a left-handed chair, things that are up will stay up. Things that are down will stay in the down position. But axial flips to equatorial, and equatorial flips to axial. So axial flips to equatorial. So this would be a right-handed chair and a left-handed chair. And equatorial flips to axial. But up stays up and down stays down. So let's go in and label our substituents via axial up, axial down, or equatorial up, equatorial down on our right-handed chair. So this bromine is in the axial up position, and then the hydrogen is in the equatorial down position. On carbon number 1, on carbon number 3, the hydrogen is in the axial up position, and the chlorine is actually in the equatorial down position. So, going to carbon number 1, what is the up bond? The up bond is now the equatorial bond. So I could label these equatorial up and axial down. So if we want the bromine to flip from axial to equatorial, but stay up, it would just go on the equatorial up bond. So the bromine would be drawn on the equatorial up bond, where up stays up, but axial flips to equatorial. And then the hydrogen, which was equatorial down, now going to move to the axial down. Equatorial, flip to axial, but down, stayed down. So now moving to carbon number 3. The hydrogen is in the axial up position, so up must stay up. So the up position on carbon number 3 in the left-handed chair is our equatorial position. So now the hydrogen is in the equatorial up position. So once again, up stays up, but axial, flip to equatorial. And now our chlorine is going to go in the down position. This time the down position is the axial. So chlorine is going to go axial down. Where, say it with me this time, say it with me, down, stays down, equatorial, flipped to axial. That is it. That is all. That is how you perform a chair flip. I hope this was helpful, and I hope this makes sense. If you have any questions, please leave them in the comment box down below. That is pretty much all that I was going to cover today. The final thing that we have to do, but I'm going to make a separate video on that. Honestly, I might just kind of touch on it right now. Okay, well, let's touch on it. Stability of chairs. In summary, you want big positions in the equatorial position. The equatorial positions are spacious. The axial positions are sterically hindered, okay? So let's draw a right-handed chair. And I'm drawing this chair in the same fashion that I showed you at the beginning of this video. So once again, please go back if you still are confused. Okay, let's say there's a T-butyl on the axial position of carbon number 1. This sucks, okay? 4, 5, 6. Because this axial position, so these 3 axial substituents are going to feel steric hindrance with respect to the big group in the axial position. So what do we want to do? Well, we want to move it to the equatorial position. How do we do that? Well, we got to perform a ring flip. Because what does a ring flip really do? It moves all of our axial groups to equatorial positions. Perfect. So to eliminate the steric hindrance, all I got to do is do a ring flip. Drawing my left-handed chair. I will label my carbons, starting on my right-handed chair, in the clockwise direction, 1 to 6. Now for my left-handed chair, I must start labeling 1 carbon over in the clockwise direction. So carbon 1, 2, 3, 4, 5, 6. So now on carbon number 1 in our right-handed chair, the T-butyl is axial up. And then there's obviously a hydrogen in the equatorial down. On carbon number 1 in our new chair, what's the up position? Well, the up position is the equatorial bond. So the T-butyl now be drawn in on the equatorial up position. And the hydrogen will be on the axial down. So now that we've moved this big bulky group to the equatorial position, there is less steric bulk, less steric hindrance, so the complex is more stable and happier. So this would be the best, most stable chair. So you got big groups, put the big groups to the equatorial positions. And that's pretty much it for the stability of chairs. It's really as simple as that. You want to put your big groups in the equatorial positions. If you have more than 1 big groups, then you want to put the biggest group in the equatorial position. Obviously, the best case would be to put them both in the equatorial positions. But if you can't, then you want to choose the larger group to be placed in the equatorial position. That's pretty much it. That's pretty much all. Thanks for watching this video. Please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content and you find it helpful. And have a great day. Bye.